Welcome everyone. Very happy to have Alok continuing this series of lectures.
Thanks. So I'll just continue with where we stopped last time. We're going to start looking at the source of the problem of IR divergence. So where the problem emerged, and so again we will just to begin with we'll focus on scalar QED. But this goes through verbatim for perturbative gravity also, what I say here. So the real issue which was really first noticed by Coolidge and Pradeep is that at least there is a mistake we make in developing scattering theory when we have massless particles. And so at this stage it's important to note that we are not trying to look for a higher finite S matrix, we are just trying to define S matrix by correcting some error. So it's not like we have some arbitrary thing in mind that we want something which is higher finite, but that turns out to be almost come out of the analysis. And so the source of the problem is the following: that you just look at the interaction potential, at time t, which is given by. So we are just looking at where J is, as you know, 5 star. And so when I write this in momentum space, it's a 3-point coupling. So I'll write one term. I mean, there will be, there are many terms coming from particle and antiparticle contractions. But so we have 3 momentum space integral. So K is the momentum of the photon, massless photon, and then you will have a term like, for example, B dagger P, Q. Let's say this is the creation annihilation operation for the particle, and then there will be a C dagger C for the antiparticle, and you have EK, and then you will have e to the minus I EP minus EQ minus EK mod K, and then I integrate over. Because I have to integrate over space, and this integral will just give us a momentum conservation. So I just write that down. That will give me delta Q of E minus Q minus K. So that's plus other terms, many other terms. So I just this. So this is just the usual thing we will do. And now we notice that okay. So first we can just solve for one of the Q integrals, and this will give us. Maybe I solve for the P, and then we have P dagger Q plus K, EQ, EK, and then we have this exponent which typically will so EQ plus K minus EQ minus mod E, and that's other stuff. All the other contractions. But you see that now if I notice this guy, because there is a B dagger and a B, there is a relative sign difference between the energy associated with these particles. And if your theory did not have a mass gap, instead of mod K we had an EK, then this exponent will always go to 0 at late time. But now because the energy, because these modes don't have any mass gap, for small enough mod K this exponent goes to 0, can go to 0. Because if mod K is very small, then this difference cancels. And so the statement is that now if I look at VPS equals to infinity, then this interaction potential no longer dies down, and precisely because of the contribution of the soft photon modes. But already at this stage we notice that this is a bit heuristic because we are not exactly able to say what we mean by soft here. So this is the schematic thing that sort of make little bit put little bit obstruction in Coolidge for the implementation of their idea. But I hope roughly that thing is clear that if I just schematically write this as soft integration over soft modes, then I have my potential goes as integral QQ integral soft K, and then in the I will get Now there will be many terms. I'm just writing the terms directly. So you can check immediately that after some algebra you will get e to the I q dot k by q e minus e dagger k e minus I q dot k by q. Sorry, this should be plus e multiplied with the charge density. So which is just b dagger b minus c dagger c. So this is the late time interaction potential, which is different than what we will have if theory had only massive particles. And because of this, now what they realize is that so our asymptotic Hamiltonian is not simply free Hamiltonian but plus late times. So maybe I write it here. And so at least this is a mistake we have committed in looking at developing scattering theory in QED. So that we assume that the particles are free because they're eigenstates of H0, but we shouldn't be doing that because we have this extra contribution also. And so we should really be diagonalizing this H AS in QED. And then, okay, now you just play the usual game we play with. Yes.
Whenever you have massless particles, this is true. I mean,
yes.
Doesn't matter whether it's gauge field or not.
Yeah, even for scalar field theory, like phi cube, massless phi cube, this would be true.
So, in Goldstone boson theory, probably there it's different. There the couplings go to zero or something like that.
Yeah, that's a good point. So there the interaction potential will not. Yeah. Well, I mean, if you look at low energy theory of motion bosons, that will still have higher divergences, I would have thought. I mean, the EFT of pions, for example.
Yeah, I was thinking it was better there because the couplings, interaction couplings also.
Yeah, but scaling momenta, so there will be no divergence, you're right. Because there will be, we will never have a, we never have a polynomial interaction.
Right.
Yeah, at least in 3+1D, there are no IR divergences in the pion Lagrangian, massless pion.
Right, because of the derivative couplings, right? Because all couplings, all the interactions are derivative interactions.
That's right.
So,
Sorry, and just to pursue this, in gravity, once again, you expect couplings to go to zero at zero energy. That doesn't make things better.
No, so it will be similar except that we will have a stress tensor, I mean here in energy density.
Yeah.
And then this will be the, sorry, I should have, so this is really, this is a mu k, with the current of course, so there's q mu. Sorry. So a mu k, so in the gravity case it will be,
right.
Yeah, q mu q nu and a mu nu.
You're saying the important thing is that the derivative is a q, not k.
Exactly, exactly. Yeah.
Fine.
Alok, I'm very sorry. I somehow lost track of your seminar being now, so I'm joining from Zoom. But can you just briefly say what is VI? Sorry, everyone. Just one sentence.
No. So VI is just the interaction potential, and we want to study it at late times.
Okay.
So the statement is that because we have massless particles, it doesn't go to zero.
Okay.
So our asymptotic Hamiltonian is not free, but it's this it has an interaction, some remnant of the interaction.
Okay. Thank you.
And so then the statement is that now if you look at the Coolidge for the idea was that let's look at the evolution operator. So you want to solve the equation which is partial u asymptotic by partial e is I h a s UAS. And then I will skip all the details. I'll just tell you the final answer they found for this.
Sorry, just one more. When we study undergraduate quantum mechanics, we learn that if you do, what we're saying is the perturbation theory is degenerate, right? Because if G is zero, then H0 is fine.
Exactly.
All of these effects turn on the G.
Exactly.
Now, when we learn undergraduate quantum mechanics, we learn that perturbation theory is very tame if it's non-degenerate.
Yes.
But it's more interesting when there are degeneracies.
Yes. And then we choose states.
Right. So if it's degenerate, you just change the energy level. Nothing much happens.
Right.
But if it's non-degenerate, you can suddenly move your eigenstates can really move around.
Right.
if it's degenerate.
Yeah, the whole time.
Yeah. So basically that's what's going on here, because you've got these massless particles give you a degenerate manifold.
Yes.
And then you've got to choose in this degenerate manifold, you have to choose your eigenstate property. Is that?
Yeah, I would say, I would say, but except the fact that what makes it more complicated is that the states they find do not belong to the Hilbert space that you start with.
Hilbert space. Okay.
I mean, they are not in the Fock space of the free theory.
Means they're infinite.
They're infinite now. Yeah, that's the only. So it's not. It is almost like that, but.
Okay. Okay.
No,
But if you
yeah, go ahead.
put an ion cutoff in a box, then it would be exactly that. Or all of these divergences will be with volume.
Exactly.
So let me think of it in a box 1 million light years. Then it would be exactly that.
Yeah.
Okay, fine.
Yeah. So you're saying that somehow I put the cutoff on K. It doesn't go to 0, but it goes to epsilon.
Yeah.
Some epsilon. Yeah. Yeah. Then of course there is no problem.
Right.
Absolutely. I mean, it's very large norm, but it's not infinite.
But it'll be almost bigger.
Almost.
So as long as G is larger than the gap between these things, it'll once again be
Yeah.
degenerate perturbation.
Yeah.
So it's just that order of redundancy.
Yeah.
What is G, by the way? I can't see it on the board.
It's not
Coupling
there.
constant?
QED coupling. Yeah.
QED. Yeah. So sorry, I really am sorry for interrupting. But just to say, I didn't. I mean, always in scattering, right? You have near degenerate states because asymptotically e to the I p dot x, as Shiraz was, I think, saying, if you are in a very big, in the continuum, you will have near degenerate states, right? So that issue we know how to deal with. You use Fermi golden rule, right? You have to sum over states and so on. There's something more in QED. No?
Yeah.
Am I missing something?
I was saying that let's try to look at single particle states, for instance.
Uh-huh.
Your single particle state, of course, there's degeneracy, but once you fix a conserved quantum number, namely k, then you break that degeneracy is gone, right? No, normally. Now you got this k, but you can dress it with soft photons, which preserve that k. So even in finding single particle states, now you've got a degenerate problem, right?
Yeah.
That's what
Yeah. So that's all I was saying. There's something more than just the continuum degeneracy in QED, right? Which is the multi-particle aspect.
Yeah, it's the more is coming because you've got this massless particle.
Yeah.
So in defining single particle states for the massive guys, there's that degeneracy.
There is a degeneracy.
So I mean, no, it's not right. Just to say what the single particle state is requires you to solve that degenerate perturbation theory problem, right? More or less.
Yeah, I agree. I think this is spirit. Yeah, exactly. Yeah.
Okay. Mm-hmm.
So now we want to understand what this asymptotic evolution operator is. And
so just to finish that, if it had been like if the photon had a mass, then the next state with k would have been separated from the one particle state with a mass k.
Yes.
Because you would have had k, q and minus k.
Exactly.
Each of them would have had 2a.
Yes.
So that's
right. Yeah.
Sorry, I couldn't see much. So let me just ask. So this has nothing to do with the massless particle being a photon.
No. Just that the mediator is a massless particle is all we need. Exactly.
So same issue.
Exactly. Yeah. Even phi cube, massless phi cube, we have. And so now the point is that so now we want to do what we usually would do, which is to solve for the So in the standard theory, HAS is just A is 0, and then there is nothing to solve because in the theory with mass gap, if M was not, there was no zero mass particle, then UAS would simply be E minus I H naught C. So the asymptotic dynamics will be the free field dynamics, but here it is no longer true, and so we can just write down what the AST at large time. And so here is where we are being schematic right now, because we don't know exactly what this means, we just mean at a very, very late time. But this is something we will try to make precise. And so this is simply time ordered exponential minus I integral. So maybe I should write T dt prime H. Okay, so that's our this is the dynamics that we have to append. So the Coolidge-Faddeev idea was that your states should be, you take your free field states, so psi naught, psi in for example, and you act with them with the U asymptotic. And this is what you would call a dress state.
Just
Yes, yes.
one kind of continue.
Yes.
Continue on this point. I mean, in supersymmetric theory, sometimes you have moduli, right? Moduli.
Yes.
And those are
Yeah.
really similar kinds of things. But there you talk about some super selection sectors where
Yeah.
you fix the moduli.
Yeah.
But this idea would say that this issue would come up there also, right? And there you would say that don't want to fix somehow super selection sectors, right? I mean, is that and
You are
associate hyperspace to a particular point in the super selection
Yeah.
sector. But now we want to say that we want to move away from it. Is that?
But here you are saying that we can't. Yeah. I mean, you are ruining my punchline. This will be the next talk. I mean, the idea is to make your idea. Can we implement the idea you said about just think of this as moduli in some space of Vacuua, precise, and which we are unable to right now, I think, satisfactory in QED. But idea is exactly that. So here we are not. You are right that you give me one charge density, one configuration of charge particles. I mean one sector, because this dressing is dependent on the configuration of your charge particles. So for each, so you start with some incoming states configuration P1 to Pn, and the corresponding dress states is in one super selection sector. But if the final moment are something else, then there will be other super selection sector, and they are not unitarily related because they are in different moduli, as you would say. So morally, that's what we get from Coolidge for the analysis, but I think we don't understand it as precisely as in supersymmetric field case. But that is something that we would like to understand.
I mean, were you asking whether spontaneous symmetry breaking, that kind of thing will not happen? Were you saying that?
No, it will happen, but you still probably have to take into account some neighboring
Fluctuations.
Yeah, fluctuations.
Fluctuations, so the value at infinity will be fixed.
Value at infinity will be frozen, but I don't know. I mean, it looks like, I mean, you have to take into account this massless particle that moves you around, right?
Which will move you around with some k.
With some k, yes.
If you fix a k, you have broken some symmetry spontaneously.
Yeah, but I mean, I don't think spontaneous. Like we know that in 2 dimensions.
Yes.
That
You have to
infrared divergence is so severe
Yeah.
that in say computing the partition function of the theory doesn't make sense to
fix it.
But I think it's true that it makes sense to fix it in 3 dimensions.
But then this degenerate perturbation theory that you were talking about is also there, right? That issue is
It's
also
in
there.
states, but not in these boundary conditions for the partition.
Yeah. Can I make one comment there, if I may, towards Abhijit's question? At least in all my understanding, you're right, you get massless moduli, but they are typically paired with Goldstone modes supersymmetrically.
Yes.
And so what happens is what protects the Goldstone modes vis-a-vis infrared also ends up protecting the moduli, in the cases I know. But you all can tell.
Something like a parallel story here. When I discuss asymptotic symmetry, there are the soft modes and there are conjugate pairs for the soft modes.
But I think they're asking different questions. They're just asking about the expectation value at infinity of a scalar field.
No, that's not what I'm asking. That's obviously fixed. I thought Abhijit's point was that given a particular vacuum, you still have massless particles. So why doesn't that cause a non-trivial dressing problem? Was that the question or not?
Yeah, and then how do you address that problem?
Yeah.
There is presumably a problem of
That's what you're asking.
similar kind. And how do you address it?
So sorry, then I misunderstood. I thought that for each, what we are saying is that you give me some configuration of momenta, and then I'm going to give you a super selection sector based on this configuration of momenta. And so then you have infinitely many super selection sectors. You are saying something else now.
Yeah, I was saying something else.
So can you say? I mean, so this is not a sector for you, is it? Is that?
No, not by. That would be a state in the super selection sector.
Yeah, but I'm saying that this state, if you change P1 to Pn, the state you get will be orthogonal to this state. They are in different super selection sectors in a.
But state being orthogonal to this is different.
And they are in different Hilbert spaces.
different Hilbert spaces.
Yes, in that sense.
Which and which? Sorry.
Like if you changed, so this dressing here, how much of a soft photons you are producing depends on the configuration of the charged particles. So if you change the charged particle configuration, then the soft photon configuration changes. But each soft photon is infinity wavelength mode. So changing that is just basically giving you completely a state which was not in the initial Hilbert space.
Yeah, but isn't similar thing happening in this case where there is a modulus in some supersymmetric theory of?
Yeah, I thought it's similar. I mean, that's why I understood that it's similar, right? So here we also say that, as you know, that the spontaneous breaking of asymptotic symmetry gives you these Goldstones, which are the soft photons of soft electrons.
It's like the scalars in any cosine.
Yeah, scalars in N equals 4. Yeah,
They probably have the same issue.
it's the same issues. Right?
Right.
And then you would probably say that these dress states are in some different Hilbert space than your ordinary states.
Yes,
Right?
certainly.
Now that Hilbert space is because your original notion of superselection sectors were incorrect, right, in some sense. Because you have to.
I mean, originally we had no super selection sectors in some
Proving
sense.
showers, including those moduli also.
Okay, but so I'm saying in QED before these dress states we don't have. But one mistake we made was we ignored all the super selection sectors, which is why we always got zero S matrix. Because the higher divergence was killed the S matrix, remember. So the point is that we are always saying if you assume that the in and the out state are in the same super selection sector, we are getting infrared catastrophe. And so this is the error we have committed, that we should realize that we are necessarily going in a different super selection sector.
I mean, when you say super selection sector, what do you mean?
I do mean that configuration where you fix the boundary conditions.
I think you mean different things.
Okay.
No, but that's what I'm saying. Maybe there are the same issues.
I see.
That's what I'm saying.
I see.
I think I also feel, when we discuss maybe asymptotic symmetry, it will be more connection will be more transparent.
You should go on. What are the two different notions of superselection sectors? I mean, I thought in theories with moduli, you fix the sector by dictating the boundary conditions, right? If you can do it in higher than 2D. Isn't that the notion of superselection sector? Or is it something else? Just once.
Yeah, I was thinking that if you start thinking about a scattering problem in this supersymmetric theory, where you are working with such notion of superselection sector, these issues will again hit you, right? That there will be higher divergences and so on. And the address, and the way you would address them would be to kind of use these dress states, which would not live in that superselection sector, but some others.
I think.
Yeah, that's true. But I just want to say one small thing. Of course, if your underlying theory is scale invariant like n equals 4, then we are not going to try and attempt to define an S matrix or anything, right? But
what's a Coulomb branch?
If you go on the Coulomb branch, okay. All right, okay, that's a good point. Otherwise, what I was going to say was oftentimes you'll get the non-Goldstone mode paired supersymmetrically with the Goldstone mode. And that helps with its infrared divergent properties, at least in the cases I've seen. But okay, you're right. You could just go to the Coulomb branch, but we don't, I see. There also you'll get, but then you'll have masses for a lot of the scalar fields, right? Okay, you'll still have the massless.
Moving the Coulomb branch moduli.
So you say you have to dress them up like that. Okay, I see. Okay.
They're supersymmetrically related to the photons, right? So it feels like whatever.
They're supersymmetric. Yeah, you're right. Okay. Thank you. I see. Okay.
So the idea of Coolidge-Fuzzy was that what you want to do is to evaluate. So this is the idea, that you take some dress state for some out dress state, take your Dyson S matrix, the one that we usually have, and this is the object you should evaluate always, because these are the correct scattering states. And so now the question is, when we evaluate this quantity, is this IR finite? And I'll give you a quick argument as to why, naively, formally, this thing would be IR finite, but only at this stage, very, very formally. So, yes.
Can you define? I mean, can you say what you mean by Dyson S matrix?
Yeah. So that Dyson, I just meant the, it's just the, okay, I will write it like limit P 1 going to infinity, you had T1, T2, where you had T1, T2 is our the I H T1 minus T2 the minus I H naught. That's the standard.
And what is H? I mean, in HAS, what?
So HAS is just the lifetime limit of H.
And what does, I mean, is there a formula for that?
Yeah, so that was the one that, sorry, I deleted.
That's what you.
Yeah. But modulo all the caveats, I mean, it was very sketchy because I said over soft and all. I mean,
Yes.
right? So we want to make that more precise.
Okay.
And if we do not make that precise, then we have, in some sense, very scheme dependent answers for things. Like how we define soft will tell us some different estimates.
Yes. But just for a moment, sorry again to interrupt the long distance, but along those lines, I mean, the UAS only has, seems to have an integral over T, but only has HAS. So is the idea that HAS is what happens to the interaction at late time, but
Exactly. So somehow we want this T to be very large. So we want to somehow, I will say more about this. So that's why this is little formal. We want to say that we want to, that's why I didn't put any lower limit. So we are saying that we are only getting contribution in some sense from the upper limit at very, very late T.
Okay. So UAS somehow starts off the lower limit.
Exactly. We want to say it starts off at some T naught, and this is ad hocness of Coolidge for the West, in my opinion, where T naught has to be in some sense very, very large.
Okay.
Doesn't account for scattering, it only corrects the asymptotic state.
It's only, exactly, corrects the asymptotic. So T naught in some sense large.
Okay.
Yeah.
Thank you.
So So the whatever T naught we choose, inverse of that will put a cutoff on the softness for us. That's the basic goal.
Okay.
Your definition of the Dyson matrix that replaced 0 by H asymptotic, then I could have done that and not use the rest case.
So I deleted something here. Sorry. You were
Here, when you deleted the definition of Dyson matrix, you define it as e to the minus IH times
yes.
e to the minus H.
So now what we are saying is we want to replace that H naught with HAS.
Yeah.
So, okay. Thanks. Okay, I can do that. So that's exactly what we mean by this. Because what is this? Is this is psi out. You had AS, which depends on the out states, of course. Dagger SB UAS, which depends on the in state. I2. And so now you can just show that this is same as exactly what you said, which is e to the IHAS T1 minus T2 e to the minus IH T1 minus T2 and the minus IHAS T1 and limit T1 T2. So wherever we have H naught in our formula, we replace it with HAS. Like that's the only change that occurs. So let me just write down the exact formula for this.
The fact that you're doing QED also now becomes clear that it's really simple, right? Because let's say if you were doing QCD or n equals 4, there will also be interactions between A's and X's.
Exactly. That's it. This absolutely. Yeah. So this idea, one of the criticism of this idea was that we don't know how to apply it for QCD exactly.
So at the moment you only have a mixing between a one particle electron and a two photons. Is that right?
No. We have mixing. Yeah. Let me just write. Yeah, no. That's a great point. So let me just write down the rest states to give you an example. So let me write. Let's take a two particle state, some electron positron state, for example, and let's write down the dressing for this two particle state. And this dressing we can show that this is given by. So I will write it in two. So what is happening is that we have to. Yeah. Let me write and then I will explain it.
You say you act again on a 2 photon state that gives you a 4 photon state.
Yeah. And also we will. So this is given by.
That's close.
Yeah. It will be given by. So we have this integral. One photon, but there will be Coulombic interaction between the yeah. So we have summation over both the particles. So I equal 1 to 2. Then we have what I wrote down earlier, which was Pi mu. A mu to the I pi dot k by omega I t minus conjugate times whatever the charge. So charge. So this is my electron. So okay, I put qi. I will put charge as qi. Term times a phase term because of the fact that actually what we had was in the exponent we had a sum, and so we get an extra phase which I just write as exponential I phi t1 p2. Acting on p1 p2, and I now write down this phase. So this phase phi p1 p2, it just comes from the BCH formula because we have like a rho. So we have to just look at the commutator, and then will give us one phase like this, and this phase is given by exponential minus I t square integral dq L by 2 pi q p mod L p1 dot p2 divided by p1 dot L plus I. Okay, right now it's just. So if you remember, this is like the Coulombic phase of the thing that we found there. And so this is the full dressing. So this is telling you that the dressing cannot be individually exercised on the particles because you have the interaction between them, and then there is this. So this one has no photon operator. So this is like just a just a phase, but this one produces soft photons.
Right, so you've taken this and acted on the bare two particle state.
Exactly.
And the action you say is because A was like a coherent state?
Exactly. And so we have e to the time order e to the I integral of this HAS to prime. And then we have to do some BCH or some kind of expansion. And so then that you can show that it will,
Like Wick's theorem, like you get a 2.5.
Precisely, exactly. And then you just simplify it in this way.
So this dressing depends on the coupling constant, doesn't it?
Yeah, exactly.
So in particular, there's a one parameter family of dressings.
Exactly.
Each one of these things does the job of making this IR finite.
So I guess that because we're in the IR, so I think at least this is not getting UV renormalized, so it's insensitive to the UV
What I'm
renormalization.
getting at is that in particular, if you have zero coupling, then of course it should not work.
So this coupling is the same as the coupling of
It is the usual coupling, right? E.
That's what I mean. So
Yes.
suppose you're just doing a theoretical exercise
Yes.
of seeing whether it is a IR finite or not.
Yes.
In particular, so you're saying for any E which is non-zero,
Yes.
it makes it IR finite.
Yes. It's just the same E as we have in the Lagrangian, of course. So we have a Dyson S matrix which depends on a E. That same E should, of course, appear. So that's where the IR cancellation will occur.
Oh, I see. So the divergences themselves are of course not there if it is not covered. Yeah.
Oh, sorry. Okay. Yeah. I misunderstood.
So look, this is kind of expected, right? This is saying that the dress states then are basically these showers. That's
Exactly, the first one.
Then the bending is the second.
Exactly. Except the fact that this is sketchy. So this is all I want to say right now. It is sketchy for two reasons. That we can say that this is from 0 to this cut. We are integrating over soft photons, which means 0 to some delta. But as soon as I put a delta here, then my S matrix is breaking Poincare invariance. So then if I define this guy, where this is explicitly dependent on some cutoff delta, hard cutoff delta, then this S matrix is not Poincare invariant. And now you could say that, okay, I don't want to do that, I'm going to take this to infinity, because anyway I'm going to somehow, this is producing for me only dominant contribution at late times. But if you do that, then you can show that then this shower contribution is UV divergent, is an additional UV divergent. So at this stage in Kulish-Fadil, if you look at that work that was done after Kulish-Fadil proposed their analysis, people just took a delta here and then computed the S matrix and then said, okay, we have some answer for S matrix, but then it's not very satisfactory because who told us what is delta? And we don't have a manifestly Lorentz invariant S matrix element. I will just mention one work which was done after this, after the definition, where two authors showed that if you just compute this with some delta cutoff introduced for the dressing, and you just take the cross section, only the cross section, don't just mod square. Then you can show that this is same as the sufficiently inclusive cross section of Weinberg. Sufficiently inclusive cross section of Weinberg, which was also parameterized by some cutoff delta. So if you put the same cutoff, so if you say that my soft photon, I am only integrating over soft photons which are not been able to resolve by the detector, then of course it's a nice thing that okay, you got this. I mean, it's expected is higher finite, but it's also okay. It's a bit pleasing to see that I mean, intuitively it's completely clear because what this thing is doing exactly what the inclusive cross sections are doing, right? It's cancelling the divergence. But okay, at least it's nice that Pulishpadev didn't. They didn't put anything by hand in some sense to get higher finite S matrix. They just investigated the procedure carefully, and some sketchy answer they got, which has a potential to be nice. I mean, and now I just to say that we will look at it more precisely, but really the upshot of Schwartz and Hopi's work is that which is an important point, that Pulishpadev ideas are essentially correct for QED. By essentially correct, I mean all these sketchy things they want to improve on, but the mechanism, of course, as you guys are also saying, will be effectively the same. But we want the Poincare invariant S matrix, which should not have all this, problems about how we define this shower, etc.
Right. That bottom thing is that's just the action of two particles going along K1 and K2, P1 and P2.
Exactly.
Because of the exchange.
Exactly.
Yeah. It's a classical.
Yeah, exactly. Yeah, exactly. This one.
So it's classical action for this trend.
Yes,
right?
yes, precisely.
Okay, and now you've given what? You've not written a formula for the state itself. So what is the right eigenstate? So to find the eigenstate.
No, there is none, because the point is that the photons here have finite momentum. They are not zero momentum, so these are not momentum eigenstates now. The dress states are not momentum eigenstates. This is part of the problem.
Well,
because we have because of the fact that we have if you have exact zero frequency contribution somehow, then you would be momentum eigenstates. These are approximate momentum eigenstates.
Okay, suppose I was in a box and I was addressing the problem of computing I have the free theory.
Yes.
With two particles.
Yes.
And I want to compute the eigenstates of that in a very big box.
Yeah.
That has an answer, right? That I can
yeah. So we can write down the states. Okay, I see it. You are saying what are these states exactly, right?
Yeah.
So in perturbation theory, we can write this down by expanding this in perturbation theory. So let's just do that. So
is it just that we know the A, we make the A diagram, more or less, and then it becomes a coherent state?
Exactly. So there is an integral here happen over T, the late time T. So let me write down. Let me write down now this answer. So that would be useful actually. Then so let me write it in perturbation theory. So P1 P2 dressed is, I will write some terms. P1 P2 undressed plus IE integral dq k by 2 pi q p mod k pi mu by pi dot k summation over I, and then we have qi charge qi, and then we will get p1 p2 and k photon with some helicity h, and I sum over the helicity also. So this is contribution to linear order in the coupling just from the first expansion term here.
Yes.
And this p dot k came because of the light time integral over t that gives us this. So actually with a dot epsilon and mu h.
But I was wondering if you did the whole sum, does that resum into some coherent states of the photon?
No, not that I know of.
Oh.
Not directly that I know.
I thought that intuitively it seemed like you're just doing classical dressing.
Yeah. I see this part. And we have photons emitted, real photons being emitted from here.
So that's the
problem, right? We are adding, right? Like at each ordering coupling, we get 2 photon, 3 photon like that.
At least that second term should just be the coherent state. So
That's completely in terms of the coherent state. I completely agree.
But there should be a path that's coherent state, but you're saying the path that's a little.
Yes.
Okay. Thank you.
Yes. There's part which is coherent state and the part which is dissipative in something.
Yeah.
Yeah. So this plus extra terms.
Sorry, Alok, very sorry. May I just ask a question about that second part? That phi part also comes from the same HADS, right? If I understand.
Yes, from the commutators. Yeah.
So
we applied TCH formula. I mean, because we had like in the exponent we are summing over different particles. So we just kind of say that okay, we are addressing each particle, but at the cost of introducing some extra commutators in the exponent. Actually, just this. I mean, we had e to the a plus b type stuff, and we just wrote it as. I'm saying it formal. We had standard expansion.
Okay, now I understand.
I think this Magnus, I don't know, it's called something else, but it's like essentially BCH type expansion.
Baker Campbell Hausdorff. I was trying to decode in my mind. Okay, thank you.
Yeah.
Now, if we just had a classical current, some classical conserved current coupled to electromagnetic.
Yes.
And we want to find the electromagnetic state as a response to that.
Yes.
That is a purely classical problem, I would have thought.
Exactly.
Unless there's this other thing, this creation. Anyway, that would be a coherent state, right?
Exactly.
So why isn't that this?
But
because nothing's really happening with matter, right? It's not like you're changing the matter particles around in what you did. I thought they were just. I mean, the difference between quantum matter and classical matter is that the matter responds, but I'm not seeing any response of the matter here.
So you see how this term came? Is that what you're asking somehow?
No, I'm saying that if you agree that if we turn on a classical source for electromagnetism,
yes,
and the response to that, the sort of ground state response to that would be some coherent state.
Yeah.
Then it feels like the same thing should be true here. Unless you're somehow accounting for the fact that the matter is dynamic, but I'm not saying that in your
You are saying why are the photons being emitted?
I'm not sure what I'm saying. Well, I'm saying whatever you do classically should be true here.
So maybe this will answer your question. So if you did not have, I mean, if I just have a particle with momentum p and p1, and you can, of course, if you just say that it trivially scatters into p1, nothing happens to it, then of course this term cancel out. So this term will matter if you really have dynamics. So your initial and final peak momenta are not the same somehow. So you will need interaction for this term to actually manifest itself. I don't know if that answers your.
Yeah, let me just ask again. Suppose this in your theory you've got matter quantum.
Yeah.
And gauge bosons quantum.
Yes.
Okay.
Yes.
But suppose I make the matter classical first.
Yes. Sure.
So I just make some background.
Yeah.
And then I ask, given that background source, okay.
Yeah.
I ask for, I don't know. Let's say I make it just vary in space.
Exactly.
This thing just vary in space, and I ask for, so there's a time translation invariance, and I ask for the ground state of that problem.
Yeah.
I would have imagined that would somehow be some sort of coherence.
I would agree, yeah, exactly.
And I'm asking, then is the same thing true here, that these guys here are also coherent states?
I mean, formally it is, because of the fact that this is that in the sense that you are asking that these are, they are photon coherent states, of course.
Yeah.
But somehow you are saying that why we are not able to resum them? Is that
why aren't you writing it as a coherent state?
Yeah.
I mean, in other words, the Qi there is an operator at this stage.
No, Q is exactly, it's operator.
You should replace it with a number.
Yeah, so that's what I've actually done here now, because I've started with
that does look like okay.
Yeah, it's coherent state, but I think Shiraz is asking, but this is operator, so it's is that what your question is somehow? It is a coherent state.
It should have the operator there.
Yeah, so, but no, Shiraz is saying something else.
No, I'm saying just this, it's trivial. What I'm saying is trivial. I'm saying that the final dressed Faddeev-Coolidge state, isn't it just a coherent state corresponding to the classical solution of these two particles?
And that is not like that because it's e to the power.
No, I mean, I presume it is. I just on this side he wasn't writing that.
Expansion.
I expanded it, but
But if you didn't expand it, this would be the example.
so then it would be, this would be our answer.
Yeah.
Right? But yeah, I just want to say that, you know, this dressing, what this dressing is telling us that so we have, you are right, that we have some coherent state of photons which is dressing each particle,
Yes.
and then we have a pi which is like
In
that.
general, in a coherent state, you have e to the, say, alpha times a.
Yeah.
A is an operator and alpha tells you what's the 1 point.
Yes.
Exactly.
So is that, I think.
Yeah, it is like that. If you exactly, because if you fix the matter state as Shiraz is saying, then this becomes a number.
Right,
Exactly
right.
as you said.
So everything else other than the a mu there is like fixing the 1 point function.
Exactly.
And that's the classical answer.
Exactly. And then only this part is maybe from that perspective a little more, Shiraz.
Yeah, I'm wondering where did that come from? I mean, from this. Why isn't it all in this coherent state?
Yeah, that came just from the time ordering. I'm saying that we,
Time ordering.
Say that. Yeah. So we just have because we have time ordered exponential I integral t.
You're saying in the 2-point function.
Exactly, the 2-point function, and that's the only thing that survives. So we have this AKST prime, dt prime. So you know, I'm just writing it schematically. We wrote it as exponential I integral t AST prime,
Yeah, very nice.
and then the commutator.
Very nice. So this is like quantum fluctuations.
That's the quantum higher order.
Yes, I
I
agree.
mean, basically, you cannot quite fix the background matter, right? They need to solve the equation.
Yeah, so that's the concept part. But here there's quantum fluctuations of the photon.
Yeah. Because I think we have fixed this state. I think
This
that.
part, yeah.
Yeah.
Because it's like taking BCH commutator.
Yeah.
That's like one fluctuation.
Yeah.
The
So that the dressing operator is the operator on the full Hilbert space, but once we fix the classical.
That's very nice. So you're saying there is a number.
Yes.
That just becomes a number, right? Because it's phi commutator phi.
Exactly.
So it's a coherent state dressed by a divergence of a number.
Exactly.
Okay, very nice. That's it.
What was the last thing Shira said? That phi is what? It's a commutator, I see, and then Shira.
Therefore, it's a number. As far as phi and A and A dagger are concerned,
It's just a number.
it's a number. It's not an operator anymore.
Yeah. It's actually infinite number.
So it's just a renormalization of a coherent state.
Yeah.
I see. Okay.
One question now, if I look this this U asymptotic operator that
Yeah,
you have done,
yeah.
and I compute it U, let's say, I think you call it B, like the creation operator.
Yeah.
U, B, U dagger.
That's a great question. Yeah.
Would you get like what?
Yeah, it's addressed.
So would you get,
People have written that down.
okay, you get some Wilson line.
Exactly. I will come to that. Actually, yeah. That's a nicer way to look at this.
Okay.
Yeah.
Same.
I was just
Expectation value of
what happens?
stress energy for these stress states
Yeah.
is different from the expectation value of stress energy on the ES states.
Yeah, absolutely.
So in gravity, does it make sense?
Yeah, I mean, in the sense that we are saying that
Get a Wilson line attached.
I mean, it's divergent. Is that what you're asking?
Yeah, but then,
But that's a different divergence.
but if you're introducing some extra stress energy,
Like,
Yeah, because we are saying that our dress operator, it also has gravitational energy. If I dress it like V dagger P, and if I dress it as one card said, right? This will not commute with the gravitational operator. This will no longer be zero.
yes.
So then it has some contribution also of the gravitational stress tensor. If you compute stress tensor from this guy.
But are these physical states then? Like because you have introduced some certain amount of stress energy defining the states.
So now we are saying we can no longer think about the tensor product of the matter and gravity anymore. Because of the IR issue, we have to look at the full Hilbert space only. So I cannot no longer think of now, if I work with the dress operator that Unkar said in gravity as you are asking, it is no longer true that my states look like this. Because some part of this has actually gone in here. That's what you are asking, I think, right?
And if this expectation value of stress energy, does it account for that? Like
Yeah, because we will, what you are saying, I think, is that let's look at the stress tensor of the matter, but rest matter, and compute the expectation value. But that has some contribution of the gravitational fluctuation also. So it accounts for some IR part of the gravitational energy. So it is, I think, to leading order in dressing, people have computed this expectation value. Yeah, but yeah, I mean, yeah, we will see that Vishwadev itself has some problems. So, yes.
Yeah. I mean, I remember from some very old lectures I listened to. So I thought that somehow I just wanted to know how this infrared divergence is being cancelled
Yes,
in a finite divergent way.
exactly.
What I mean to say is that if you have a single electron state, you can imagine that it's two kinds of things happening. One is virtual photons,
Absolutely, yeah.
sticking to them and coming back.
Yeah.
And the other thing is the real photons,
Exactly.
sticking out. So somehow the
Thank you. Yeah, exactly. So what is happening is the following. Suppose I take a 2-2 scattering.
Yeah.
So P1, P2 going to say P1 prime, P2 prime. And let's look at a canonical divergence we get from a triangle graph like this.
yes.
So now this one in the excellent prescription, as Feinberg has shown also, I mean this, this one is, this is really integral d4n by 2 pi to the 4, 1 by L square plus I epsilon, P1 prime dot P2 prime,
Yes.
P1 prime, I'm only looking at the soft L, because I'm interested in the, as you said, in the, so P1 prime dot L plus I epsilon and P2 prime dot L minus I epsilon. And this one has both real and imaginary pieces because of this I epsilon here. I can break this into delta and the principal value. And now it turns out that, so think of this as having some real divergence plus some imaginary divergence, please. Now what this dressing is doing, this part cancels the real part of the divergence. And this part cancels the imaginary part of the divergence.
I see. And the real and the imaginary referring to real photons?
No. Here the interpretation is that there is no such. I mean, it is in that sense as Abhijit explained last time. It is like that because when I put this on shell, it's like I'm cutting this into 2 photons. So effectively it is that. But here it's such a computation. I have an integral like this, and this gets cancelled from both of these. Yeah. So in the usual computation, of course, as you are saying also that we compute this inclusive cross section where we take this process, we mod square, and we take a process where real photons are emitted, and they cancel each other.
Yeah.
And that cancellation is now substituted by these two. It's a goodish point.
So you discussed all this in the first lecture. I'm so sorry.
No, not this. No. This part right there.
I see.
Yes.
If you have 3 particles, P1, P2, P3,
Yes.
this phase presumably would still be P1, P2, P2, P3, P3, P1, right?
Exactly.
Not,
For each pair.
For each pair, but not like 5 P1, P2, P3.
No. And in fact,
And then how to see that from the commutative?
because it is really
From physically, it is more natural, but how is it happening?
yeah, that's a very good point. Because it is coming from rho P1, rho P, rho Q, you get rho P, rho Q, and commutator of the K mu, P mu, Q mu. So these are the terms that you will get when you do the time ordered expansion. So always get a pair.
Yeah.
You always get a pair. And now what is interesting, I didn't have so much time to go into all the detail, but here what happens is that this phase is such that if it only pairs incoming or outgoing pairs. Like there is no phase between, there is no such contribution that you can check just from computation. Yeah.
So if there were gluons or gravitons,
Graviton is exactly same.
then what Abhijit was saying would come, no? I mean P1, P2, P3.
No. In this it will not come just because this came from the term in this expansion of the time ordered product. So here it won't come just from the algebra.
But the fact that there's self interaction among the photons.
Yes. So self interaction between soft gravitons is subleading because of the soft gravitons have soft energy. So in graviton it's exactly this, except wherever there is this you have P mu touched up. Gluon is infinitely more complicated as you are saying, and none of this really works like this. Yeah. And part of the motivation of the modern development is to really capture as why things work so nicely for QD but not for QCD. Can we have a framework which works for everything? It is this Schwartz attempt of Schwartz to.
I'm sorry, the statement that the state is not in the invert space,
Yes.
that comes from phi as k goes to 0 or?
That is one. And I would have also, because of the fact that the because even the other one, because we have a d cube k by 2 pi cubes to omega k, and we are integrating over soft k dagger k, and this one creates a pole because it's the soft, right? So it also creates 1 by 2 omega k.
Sorry, this is in the coherent state, you say?
In the coherent state. So, and remember, there was also 1 by p dot k coming from the exponent. So now you see we have a logarithmic divergence also in that other coherent phase system. So both of them mess up with the.
I see. So first, the normalization is big.
Yeah.
And second, the state has lost infinite norm towards the other.
Exactly. Yeah.
Okay.
Okay. So now I will. This is related to our observation Sandeep made last time, that this complicated looking dressing, which is UAS, which is time ordered exponential I integral t pt prime HAS t prime, can be written in terms of a Wilson line, and this is also related to the what Onkar said. So let me give you the result that which is yes.
Can you just
Yeah.
show again this commutators which give rise to?
Yeah. So it is we have okay. So let's just write. So we have integral d cube q by d cube
So
k.
this is the commutator of the asymptotic Hamiltonian going through the Lyson-S matrix.
Exactly. So we have dt ds e to the rho q. Sorry, there are too many. So rho q2, rho q1, rho q2. Then we have e to the I q1 dot k by omega q1 t to the minus I q2 dot k by or maybe k prime by omega q1 q2s. Then we have a dagger k prime. So this is this one which
Sorry, what was what again?
rho is just our charge density.
Okay.
So this is the one that gives us the. So this gives the delta, and then and of course there is a q1 mu, q2 nu, and this is there is also a mu and a nu here. So eta mu nu delta k minus k prime.
It's just that
And that gives q1 dot q2, and so that gives it.
H is normal ordered.
Yes.
E to the power IH is not normal.
Yes.
So you just normal order E to the power IH, and that gives that. Just the A will be there.
Yes.
No, but you somewhere you use the fact that there are photons, not gluons.
No. Sorry. You mean in the photon case, this itself is complicated. This is not the form we will get. It will be like exponential of exponential. Because of the fact that in photon we will have, if you just look at diagrammatically, this contributes at the same order as in the soft expansion with this. So this in the gluon case, sorry, in the photon we don't have it, and gravity is subleading in.
As an operator, you'll have A cube and A to the 4 term.
Yeah, and they all contribute. Already at the level of dressing, it's not a closed, it's not a coherent state form as.
Actually,
but it has been written. Yeah.
No. I'm very sorry to slow you down, Alok. You can ignore this, but just one lingering question in my mind. Aren't gluons worse than gravitons? I think maybe Shiraz was asking.
They are exactly.
Right, because I mean, alpha S will, that coupling in that vertex will have to be taken in the deep infrared. So it's like out of control. At least in gravity, I think Shiraz was saying this, it should be momentum over M Planck. So we have hope to control, right? Isn't it?
That's exactly the point. Yeah, I think so.
Okay, thank you. Just
Actually, gluon, another problem happened which is technical, just because I just mentioned that, because each soft gluon also carries a color index. So you have so whenever you emit a gluon, no matter how soft, it rotates the color state of the quark. So if I emit two gluons subsequently also, their ordering matters, even if they are soft, because they have rotated quark differently. So even without this self-coupling of gluon, there is already a color rotation problem, which is which has nothing to do with softness of the gluon, which makes it harder to be witness. But it has been now dealt with by Schwartz and Ilya Feig and others. They have this beautiful theorem called hard-soft collinear factorization in QCD, which to all orders in perturbation theory, which is a very, very powerful statement, I think, which came out a few years back.
Sorry, initial question.
Yeah. No. Yeah.
in de Sitter, the issues about defining asymptotic states morally similar.
Yeah, I think so. Maybe after this, actually, I will come back to the parallels with the exactly the kind of things that that I think there is something to learn about de Sitter also.
Okay.
Is that right? On the face of it, I don't see it, but okay, you will explain.
Yeah, because of the fact that the in-out perturbation theory breaks down because you have the geometry creates infinitely many particles in the Adelaide time. So there is some. I will come to that maybe if I. Yeah.
Please do.
So now let me just rewrite this dressing in a slightly different way. I'll just give the final answer. So let me. We can write the same dressing in the following way. I will explain the notation. Instead of looking at a time-ordered exponent, let's just write it as. And now these limits I will explain. They will become important and I will say where they came from. So consider a charged particle. Sorry, I should have charged particle with momentum with velocity. B1. Now I'm going to define some Wilson line, and my claim is that is same as the Coolidge-Faddeev dressing, but modulo the subtlety with the limits that I will explain. So let me just write something. B1 dot. I will explain what that is. This is a new notation that I haven't introduced so far. Yeah, okay, this that's it. Yeah. So let me explain now what this means and why this is same as the so this is a velocity of a charged particle. And my claim is this is same as the Coolidge-Faddeev dressing. Or maybe it's a more precise way to write the Coolidge-Faddeev dressing, so I will just explain the expression, then it will become clear. So let me define A soft at a point X as follows. But it's really just a soft photon field. I will explain the notation.
You're saying since the particle dynamics was not important, you might as well replace them by Wilson lines for the phases, right?
Yeah, exactly. But the only thing is where this limit came from. I just explained the limit. This is the sketch. This is the input from the soft collinear effective case. Where by soft we mean that when you do integration over k, always k. So inside the integrand, and we will use this actually when we develop the perturbation theory also. Inside the integrand involving k, replace scale k mu with a parameter lambda, dimensionless parameter lambda, and only keep leading terms in lambda going to 0. Most singular terms in lambda. So this is how I have defined the soft fields. I am not integrating over 0 to delta or anything. This is over integration over the full momentum space. So everything except that the softness is of the type that whenever I am computing a correlator of this guy, I am always going to take contribution from the integration region which is shrinking with some soft parameter lambda. And now you can check that what this is doing, because if I put x as v1s and I integrate from 0 to infinity, then I get v1 by v1 dot k. And so that gives me, formally right now it looks like it's giving very close to what the Coolidge-Faddeev dressing operator was. Now let me show why it's exactly that, because again it's because this is a path ordered exponential. So if I have many charged particles, then I have to replace this quantity with, suppose I have n charged particles, then I do this.
This is precisely the classical problem that
exactly, this is the classical thing, current problem we are solving.
was replacing what you had.
Yes, exactly. So I think the way you said for coherent set is fitting into this definition directly. And now again, because this is sum inside the exponent, we have to do the VCH type expansion. And so this will give us this can be written as product over all I. Times the phase factor, which will be, let me just, I'm just writing it formally now, summation over all ij, I less than j, ij.
So the first line is normal order.
And the first line is normal order. Because it's just linear operator in the soft photon. Because as Shiraz said that we just replace already, we have in mind the matter, classical matter state here when we are defining this. So, okay, there is a nice way to derive all this from the, the justification of doing this really, if you want to know, comes from soft Coulomb effective theory, which maybe next time we can go into more detail, but right now I hope it suffices to see the equivalence with the Coolidge Purdieu dressing. And so it is a definition of a dressing. Now why it works, we have to check.
V is what, sorry?
V is, you take any velocity.
Velocity.
Yeah, exactly.
It's the velocity associated with k, right?
Exactly, with k. So, yeah, because of the fact that this is a sum inside, so I'm writing it as a product, and then I have to do this VCH thingy. So then again, a commutator. So a commutator will give me vi dot vj.
Yeah.
Same thing.
It's the same calculation.
Same calculation.
Sorry, but this,
It's the
now you have some nice Wilson line kind of
Exactly. Picture, yeah.
Why is it similar to this coherent state kind of picture?
Because it's the same. Because the coherent state also was localized around pi. Like the dressing, the jet as you talked, right, was localized on pi.
Yeah.
So then it gave you, effectively gave you this Wilson line then.
yeah.
No,
But-
I mean, from here it looks like what you want to do is make things gauge invariant or something, right?
Which one?
Because you have Wilson lines connected.
No. That's no. This is really, this is really rewriting of the Coolidge-Purdieu operator, but in a more covariant way, in the sense that we don't put any cutoff or anything. But it's
So,
exactly.
you can also think of this as you making the asymptotic states gauge invariant, or not? So from some origin.
These don't. I could have started the electron-positron pair. Unrest, no charge at all, but I will still dress it with these Wilson lines.
Actually, can I say one thing there? At least when I had whatever little I said last time, I only meant that second term there, where it is a product over the integrals, each line. So at least, there is that phi term. If you just wouldn't just attaching a Wilson line along every trajectory just be the when you say equals to the first term there without the phi terms. That's what I was thinking you do.
So I thought you had in mind this term, Sandeep, the first one.
Yeah. That's what I had in mind.
Exactly. It's almost that, right? Except that there is some subtlety that you have more than one particle, then you have to take care of the interaction between them. For one particle, it will reduce to what you say.
Okay, but that subtlety seems important, right, in getting the whole story.
Yeah, absolutely. This will really cancel the virtual part of the I divergence in the S matrix.
Yeah, I see. So this is the more precise thing. Okay, thank you.
This is a proposal for making Coolidge-Purdieu in some sense maybe more precise, and origin came from this state. But we will see how it also helps us develop some
This looks like a solution to the problem that something was not gauge invariant and you made it gauge. That was not the flavor of the original issue.
But why? We are saying that what we are saying is that the asymptotic dynamics is not trivial, and we are now saying that we have to take into account the asymptotic dynamics, and that dynamics can be encoded into a soft Wilson line. That's all we are saying.
Yeah, but I think along the lines of what Abhijit is saying, just to make it gauge invariant, maybe just that first term on after the equal to may have been enough. Shiraz, is that right?
I think Sandeep, what he's doing is dressing with exactly what you want and then computing the expectation value. And that expectation value is giving you this phi. Because
yes.
So he's got like one A with one particle, another A with the other particle, and then he's doing the expectation value, and the 2-point function is giving that function.
Exactly.
Oh, I see. You're saying because it's not a classical object. Okay. You have to be careful. I see. Okay.
Somehow you are saying that.
I was thinking, I mean, basically a bit uncomfortable as to why is it that such a simple. I mean, it's not the gauge invariance issue that I had in mind, right? If I knew that, then this is what I would try the first.
No, yeah. This is not coming. Yeah.
Solving the IR issues.
No, we are saying that. No, we are saying that
these two things corrected.
because of the fact of soft factorization. So we are saying that soft photons couple to matter in a universal way by Weinberg soft factor, and that can be completely captured if instead of these fields you have a particle with momentum. P, and this is the coupling. So this coupling is a universal coupling of a soft photon with a matter particle. V by V dot K. So you can replace all the interactions. If you can have high derivative interactions also. You can replace all of them with a universal coupling, which is V by V dot K. And that dynamic is captured by this. That's all I think.
So if you started with the gauge invariance scale,
Yeah.
it's an electron photon. Even then there is.
Yeah, we have to use this. Exactly.
For the electron positron at different locations is not gauge.
Yeah. So that is okay.
Okay, but so there, I mean, if you really want to gauge invariance, you have to connect them with the Wilson line, right? So, but just let me say what I understand of this, just about the algebra.
Yeah.
I don't know about anything deep, but algebraically, in what you did quantum mechanically, you had the particles going in,
Yes.
and that pressing that you needed to put was what the Sari Coolidge was.
Yes.
Now that dressing did not know anything about the dynamics of the particles. So this seems just like an observation that calculation is the same as dressing Wilson lines along the trajectory of the particle.
Yeah.
Pressed.
But why? I mean,
Why?
because what I'm saying is that now for gluons also you might try this.
That's the point. That's exactly the point.
It might work, but
Yeah. So that's why I didn't. So one way to understand why I said SCT is important is because one way to motivate this is to look at the interaction between soft photons and energetic particles first. So you can write down effective field theory for that, and that Hamiltonian effective field theory is this quantity here. Now you can say, okay, let me do it for gluons, where you have again energetic particles and gluons, but now the gluons interact with the energetic particles, and you can also have collinear divergences, singularities in gluon. But that's also part of the EFT Lagrangian, so or EFT Hamiltonian. So you use that to see if you can exponentiate it. So thinking of it like that really tells you that there's a potential to generalize it.
Is this really gauge invariance? For gauge invariance, shouldn't the Wilson line connect?
Yeah. That may be correct. I mean, that may come from here, but not from the.
maybe there's some reference point.
But these are all going to different reference points depending what their K is.
Yeah.
Right? So if you then connect up to some reference point at least.
Yeah, I mean that's the zero there, right? Probably.
No, but in direction it's going to K.
Yeah.
So
this guy's going there, this guy's going there.
And then there is a charged particle there, right?
no, there's a state at the infinity.
There. So now if you really want to make it completely gauge invariant, I mean, wouldn't you sew them up?
No, I mean the Wilson line I thought was from 0 to here, all the lines are like that.
We have a local field operator in mind, I think, to make it gauge invariant. Right now we are just saying we have states at infinity.
Yeah.
And of course, total charge is conserved. And then these states, we are saying that usually we think that this. Okay, let me give a picture. Maybe this. So the picture now is the following: that we are saying that we have S matrix between. This is our standard picture where we provide some states here, in states and out state. And I would have thought the gauge invariance statement total charge is conserved. Now we are saying that, but this is not enough. We have to append this with a with the dynamics coming from this asymptotic Hamiltonian or soft Wilson line in this part and also in this part. Okay, and that is captured by this. That evolution is captued by this Wilsonian effect. Is that's all yes. So we have this UAS in the past and UAS in the future. And so now, so this looks more like. This is what related to what Abhijit was mentioning.
One comment. I'm so
Yeah.
sorry to
No.
But just, I think if we did this kind of thing in n equals 4 units, it looks like you're going to infinity, but there's no such thing as infinity because it's conformal. You can scale it. It's like on the boundary of a sphere and you've got open Wilson. To make it really gauge invariant, you'll have to close it. And that part is not being done here, and perhaps it's okay because it's really the IR.
I think so, yeah, I think so.
Seems to me.
I just ask one thing. It seems enough to make it gauge invariant vis-a-vis gauge transformations that vanish at infinity.
I think so. You can work in light cone gauge, for example. So even in QCD, it would even simplify. Ghosts will also probably decouple, right? So I'm saying that part is we can just take care. I mean, we have to be careful, of course, but we can take care.
Precisely, this thing will not work in n equals 4 angles because you do it on a sphere that is very large, but that's the same as a sphere that is unit size.
Yeah. Yes.
And then it's just open Wilson lines.
Exactly. Then we have to take.
Or if we didn't
close it. You have to
pure angles theory, it would be even worse because you've created a quark at infinity. That's an infinite energy state.
Yes.
So somehow it's part of something of the dynamics is going in here, right?
Yeah. So I'm saying that we are at this stage for the gauge invariance ability. I think we are in some gauge fixed combination.
I was thinking that this
To take care of the gauge that you are talking.
connecting to the asymptotic particle which is charged.
No, we have states here. No, I think this is a picture we have that our dynamics is really. So our dynamics is we are going from 0 to minus infinity, then minus infinity to infinity, and infinity to 0. So this is our contour for dynamics now, where we have this asymptotic dynamics here by the Skett Hamiltonian or the soft Wilson, right? And this is Dyson evolution. But the gauge that you are talking about, I think we just should take care of the way we would do in usual thing. We take some gauge and work with states in that gauge. So if we have ghost, of course we worry, but okay, let's say we are in some gauge where, and QD anyway ghost decoupled, so it's okay.
No, but morally speaking, I mean, just to come back to, I think what Abhijit is saying, at least it seemed to me last time, you all said that if you compute not S matrix elements, but gauge invariant operators inserted at past infinity, time evolved to future infinity, there'd be no divergences. There was some theorem like that, right?
Yeah.
Yes,
So
yes.
it's
So even Shiraz was mentioning, yeah.
okay, I don't know the theorem, but if that's the case, then if you just put the Wilson lines and dress them, you're right about it's not being gauge invariant vis-a-vis gauge transformations at infinity. It more or less sort of does what you want. Maybe you connect E plus and E minus with even a little bit all the way at infinity or something and complete it. And then it's just part of your theorem, right?
I thought what Shiraz was saying last time is that if you compute expect correlation function involving right observables, then they should be manifestly IR finite. I thought it was in that context, right?
Yeah. So, okay, if the only worry is the open ends at infinity, we can sew them up. Presumably, they won't do anything, I imagine, in this theory.
In this theory. Of course, in QCD, they would produce a huge divergence.
They would. I agree. Okay. But here, presumably, they don't do, and then it's part of your theorem, right?
I agree. I mean, it's probably the statement that those guys at infinity can be thrown away.
I'm thinking that that's what has been here. We just one naive way is we were working a fixed gauge.
The reason they are open, Wilson lines are open at infinity is because you start with this unrest state. Like this U asymptotic is acting on an unrest.
Exactly.
And this unrest state is not physical, it's not in the Hilbert space.
It's it is in the Fock space of the standard free states if you had ignored the asymptotic dynamics.
With some infinite, potentially infinite energies.
In QCD.
In QCD, yes.
But in QED isn't very much.
Yeah.
So I was wondering whether these sewed up states are more physical.
So I mean that's a very good point. I mean here I don't know because at least the attitude we will take now is that as we saw that if you think of them as coherent state, they have infinite norm for two reasons. The phase was infinite, but also the soft photon give you infinite contribution to the norm. So the way that we will look at it now is that we are really appending the dynamics through this, but our states are Fock states, just free states. So it's just a perspective, but it's because then all the completeness relation, everything is what we would usually use. But it has come at a price that we really cannot think of it as a standard time contour evolution.
So you're saying the issue of IR divergences can be dealt with in this way?
Yeah.
And then maybe there are other issues which are hidden in these unrest states.
Exactly. Exactly. I would agree with that. I mean, this is also maybe. I think Abhijit can say more about this, but this is at least I feel, try to kind of ideas he has been thinking about, and Marolf and Morrison also about this is S matrix, where the claim was that if you just as a comment, I don't know much about this, which will say more, that if you start from scribe minus to scribe plus in digital, we know there is no in-out perturbation theory. But there was this picture that Marolf had, Marolf Shednicki, and Abhijit is also thinking about something similar, that you start with a state here and you go back and you go up and then you come back. And the claim was that then the overlap between the final and the initial state is infrared finite. And it's quite incredible that I feel that something similar is at work here. So maybe there may be a unified treatment for all these S matrices in the future.
So look, this Wilson line lives on these extra contours.
Exactly, only on the extra contours.
Yeah, so that's why you were talking. Yeah.
Yes.
And then the physical state lives at the zero. I mean the creation operator is at zero, right?
Yes, exactly.
And then there is an evolution
Exactly.
with the Wilson line.
Exactly.
And then this Dyson
Exactly.
evolution. Yeah. So that's why I guess you were talking about this line. I was confused.
Should we take the norm of these free particle states seriously?
You mean just the usual norm, the usual momentum state.
Should we expect completeness in terms of these free particles? I mean, you're saying, you sort of finesse the way that you're saying actually the states are very complicated.
Yeah.
In particular, they have a very complicated norm, right? The norm will change.
Yes.
So I'm getting confused about the statement that you can actually pretend that we're living in the usual neighborhood.
No. Just from the computational perspective. I mean, it helps to do some computation. I don't think it helps us conceptually at all to answer this question. But I'm just saying that we are simply now saying that what is our S matrix? Our S matrix is going to be some let's say P1 prime, P2 prime, usual thing. Then we have the asymptotic operator in the future, Dyson S matrix, asymptotic operator in the past dagger, and some in C. But these are our Wilson line, soft Wilson lines. So all I'm saying is that now, all the manipulations we will do, we will use this as our basis to do the computation. Only at that level I'm saying.
Mm-hmm.
But you are saying that of course the physical states really are this with this, which is a complicated state.
And the question that seems,
but yes, so I'm saying that maybe in digital what is happening is that we are saying, well, in digital, I mean I'm just talking completely random things. I'm saying in digital we are saying that I cannot put my state here because then there is no in-out perturbation theory. But it makes more sense for me to put the state here, and then I can do some evolution like this. So I'm saying that here it seems like if I put a state here as Abhijit just said, and then I look at the this evolution along this contour, it seems more computationally tractable thing to do. And then the states are really situated at 0. So that there may be something deeper also which I don't know yet.
no, but I think the computational question is, should we expect unitarity with this now?
Yeah, so formally, because these are soft Wilson line, path ordered Wilson lines, so at that stage this is unitary. Right? But when it's unitary, it's infinite. I mean, the exponent is infinite as we saw. So we have to be careful with
And there were all these renormalization phases that changed it from unitary to
I don't have a
large number times.
Exactly. So at that level, I don't know. But I'm saying that.
Sorry, and that was precisely the problem, right? It's precisely the problem that those phases, that phi, was precisely your IR divergence.
But it was cancelling some IR divergence coming from SD. So the whole point is this thing is IR finite, right?
I know, but Koski's rules don't apply to this thing.
We would like, this we should discuss. But I'm saying this is an IR finite, that's a claim. I mean, that you want to understand. This is an infrared finite operator evaluated between perfectly well-defined states, and so that's a good object.
That object can be unitary, right? You can think of that as
formally, but Shiraz is saying, I mean, that's a bit. It's a composition of 3 infinite operators.
No, but it's finite now, right?
Now it's finite, but
So now as an operator from 0 to 0.
Yes, that's the point.
Finite unitary evolution.
Yes.
Okay, so then the claim would be this finite S matrix obeys Koski's rules.
Yeah, I think so. Yeah, but we have to. I mean, this has to be analyzed. But I agree.
That would be incredible.
Yeah.
Where do we cut it?
So I will show you where we cut. So we have multiple places to cut. But maybe tell me when we can continue tomorrow.
Doesn't this
as such that you define also depend on the in and out state.
That's right.
I mean, is it like, because you have this Wilson line domain, right? And
Yeah.
if I try to evaluate this guy in matrix elements of
So I start with a state P1, P2.
not with P1, P2, but something else, then it won't.
No, I mean, you just give your Wilson line for that. You start with any momentum state, and then I use my soft Wilson line to evolve it. That depends on the source, of course, on the momentum. And I evolve it, and then I go back. It depends on, as Shiraz is saying, it depends on very little of the, it only depends on the kinematics. Nothing more, right? The problematic if it depends on how these particles interacted with each other. It doesn't. It only depends on some trivial information contained in this. Because of the factorization, universality of factor.
Sorry, and maybe this is what Abhijit was saying, but these U daggers, they all come and meet at a certain point in space, is that right?
These two? So,
Can you draw the shape of those?
yes.
If there were 4 particles scattered.
Yeah. So you don't mean this quantum. You don't mean it. So if you have 4 particles scattering, then so let's say you have a So suppose you have 4 particles scattering, then the statement is that we could have a loop here, for example, which is a standard loop. So this is t equal to plus infinity, this is t equal to minus infinity. But now this soft Wilson line insertion is telling us that we can also have a line like this. We can also have a line like this. So these are the additional. Is that what you are asking for?
No, I'm just, these U's.
Yeah.
What are they?
Yeah. Okay.
Lines are coming from here to here, right?
Exactly.
Like this. So in this contour,
I will show you. Yeah.
they are coming from here to here,
Yes.
right?
Yes.
And the state lives here. I mean, the creation happens here.
Yes. So you're asking about what this does?
Yeah, just define the beginning and end points of those Wilson lines.
Yeah. So it's just this. So this is exactly. So this is t equal to 0, t equal to minus infinity. So this is one Wilson line, beginning and end point of one of them, and the other one is plus infinity to 0. That's it.
No, and in space, where are they going, please?
In space means sorry.
So as time evolves, they're moving in space, right?
Let me try to write it down. Yeah. Let me just. So let's write. Let me write the U minus AS. So that U minus AS is integrated. It's let's just say we have one part. Let's say we have one state here, just in the particle state. Then we have integral 0 to infinity. 0 to minus infinity. Yes, A soft. B dot.
They're hugging the part.
B dot A soft.
They're hugging the party.
That's yeah. So you just think that there's a particle moving freely with velocity v, and then you're touching it, pressing it with this.
And okay, so at one end it's at infinity.
Yes.
At the other end it's where?
It's at 0. It's on reference time. Reference time.
Reference
Finite.
And reference point in space?
Reference point in no. Because it's soft mode, it doesn't know anything about that because it is infinite.
So integrating over space?
Yes. Because exactly. Because this one is. So this one. Yeah. Okay. I understand how your question. So let me write it. Okay. Oh, thanks. Yeah. So this is a localized at a. This is the point at which we are evaluating it. Right. So this V mu s. This is V mu s. So that's the point at which we are evaluating the soft operator. Yeah, you're asking something else.
Yeah, I mean, I thought we were in momentum space at the moment because there was a K.
K is here. Yeah. K is in the A soft. So A soft evaluated at a point in space time, which is V mu s, is integral V cube K by the thing we have, where you have to do this soft AK 50 minus I K dot epsilon. So where this is V. Yes.
We're just following the trajectory of
It's just follow. Yes.
It follows the world line and then I see. So you're saying that, sorry.
Yeah, no, it's fine. It's only defined there. It's only defined on the world line.
It's on the world line, but I'm getting confused because we're using both K as well as position.
So here there is no k at this stage, right? We are summing over all k's
But you're going in some direction, right? I mean,
in this direction,
okay.
in this direction. Is that what you're saying?
I suppose.
That's the external momentum.
Yeah, just the external momentum velocity of the particle. Yeah.
Okay.
Okay.
So I think the picture is that the Wilson line is starting somewhere at 0 time, but along the particle trajectory, and
yes.
then it goes off to infinity, and then it starts being the initial state.
So it goes to infinity and then the particle comes back.
Particle comes back without the Wilson line.
Yeah.
And that's the open end that you're talking about.
So now the open end is effectively at a finite.
No, at infinity. No, that is where particle is created. So that's not an open end. The 0 is where the particle
Exactly.
But
is
it's a charged particle.
charged particle.
So that's a sort of an open end, right? It's not gauge independent.
well, a charged particle loop to Wilson line should be the end.
But it's end. So you create the particle here, then the Wilson line goes up,
Yeah.
joins to the trajectory of the particle, and comes back. So this part is all gauge independent, but now the non-gauge independence is here.
Well, I was thinking
Or-
of the
or
other
the-
end.
yeah.
I was thinking of the other end where now it just suddenly stops.
But it just joins the particle trajectory. It continues with the actual physical particle trajectory.
But seriously, okay, I could say that there are some, the full state is gauge invariant, but there are some ghosts that I'm ignoring. There's a VLST invariant state at t equal to 0. I'm just working a particular gauge, where I'm just thinking of it as
Okay.
yeah.
Okay. No, but I was just wondering if we did a gauge transformation on this operator, you're creating some expectation value of some operator at some point.
Yes.
Where will the gauge transformation happen? It seems to me that the Wilson line will swap with the particle trajectory and come back.
Yes.
And then the gauge transformation will act where you started with this.
Yes.
But that's where there is a psi in,
Yeah,
Yes.
sorry,
which will absorb the
Yes,
gauge
yes,
transformation,
yes.
assuming it's gauge invariant.
Yes.
So then the gauge transformation will be where the Wilson line is open, right, which is at infinity. That's what I was thinking.
Oh, I was thinking if we do some sort of LSZ type formula, where you're computing expectation values of these operators.
Yeah.
That operator, whatever you're computing expectation value of, will have transformations at the points where you started the Wilson lines.
It's absorbed by the particle.
Absorbed by the part. I was just trying to get S matrix from an expectation value of an operator. In LSZ, we don't talk about particles, right? We just talk about operators.
Yeah, operator, that's what I mean. There's an operator to absorb the Wilson line.
What does it mean absorbed by the Wilson? You mean that is a charge operator? Fine.
There's a charge.
Now it's completely gauge.
No, but it's not completely. At infinity, it breaks. You stop the Wilson line.
You stop.
Yeah, there's a one open end
I
anyway.
agree.
Yeah, there's a one open
Because
end.
there's no insertion of a particle. Oh,
That's where it stops.
I agree.
So
But I think that,
but then aren't you also inserting a phi there? Create the particle trajectory back?
no, I think you just created it at 0.
Yes.
Created the particle at 0
Yes.
in that wiggly contour,
Yes.
and then you connected the Wilson line, and that went off to infinity. And after that, the particle is free. The particle travels without Wilson line.
But it comes from infinity? The particle?
Yeah, to scatter.
To scatter. But you could create that particle at infinity by ending the Wilson line.
So the particle created at infinity is rest, not rest.
If you just think of the operator, there is a charged operator creation, then a Wilson line, and then you just stop that Wilson line.
Stop that Wilson line. I see. And then that creates something. Fine.
And also, I think there is maybe one
Particle
more.
evolution just continues, but the particle, the Wilson line stops.
I agree.
But that's okay because the Hamiltonian will take care of it. The time evolution will take care of it.
But also, this phase, the extra, if you have electron position, there is a kind of a phase connecting them. There is no individual tracing of a particle. So that also, that's like a Wilson, that's like a line ending source between the two.
Nice. That's actually exactly the picture Sandeep was.
Yeah.
Yeah, I know. Yeah.
Exactly.
Yeah. Okay, so now maybe I just tell you how to. Let me now recall the goal that we wanted to. So there are two things that we want to understand now. One, which is I think because of all the discussion is more or less clear, but let me just phrase it anyway. That this given any out state, which is a multi-particle, so P1 to Pn, and some each state, all that both at T equal to 0, is this IR finite? which in QED as we are discussing, maybe it's not very surprising, but maybe one, given the fact that, I will explain maybe next time we run out of time, that this one has actually a new UV divergence. Because these Wilson lines are very singular. In other words, what I mean by this is that, if we start with renormalized Lagrangian and defined isoness matrix, so that we have a UV finite test matrix operator which is scheme independent, but this SH is still UV divergent because of these singular lines. So we have to further renormalize it, so it makes it scheme dependent. And so this is a subtlety that we will which makes it hard to interpret this as a physical S matrix operator. But given this limitation, we can still ask the following question: that do IR safe observables computed via, okay, so if I compute, for example, so let me write the one that we will mainly discuss.
Can I just not follow that Wilson line without disconnecting it? You can just throw out, and whatever process that particle participates in, you just always accompany that Wilson line.
But we don't know that. Then we have to look at the HAS more carefully, because we are ignoring by instead all the interaction which would have appeared at finite times.
Yes, yeah,
So,
that you would not be able to do.
Exactly. So we will then make order 1 error if we just try to think of
You will get a different answer.
Exactly.
You get an answer, finite answer to a different question.
Yeah, to a different question.
Okay.
If you do too much, you get the answer.
Yes, that be one. No, that will be I think that KMOC type gauge invariant operator expectation.
Yes.
I think it will be that kind of.
No, but the KMOC, whatever S matrix you use, you should get the right answer, right? So here, so here one of the questions we can ask, in spite of the fact that SH has a limitation we will discuss, but the UV divergence is that, is this true?
No, I mean in particular it will also be unitary. So you can look at those cases.
Yes, it is unitary certainly, but it will be, we will be overcompensating for that. Yeah. So this is the question we want to ask. At least in perturbation theory, that if I compute these semi-inclusive cross sections where something is lost, some photons are lost with momentum px, is this true or not? Then at least because we know that this is IR finite, this observable is IR finite, and so this could be a good check for SH. So we will see to what extent, in what precise sense these two match or mismatch.
But there cannot be really a UV divergence because you are using only soft photons. Isn't it?
But for for the soft particles,
So you may say that there is a sort of line that you are putting between soft and hard, and that's
exactly, because we are saying that in the I give you a process like this, and a soft photon is emitted, but now we are saying that we are thinking that this process is same as this process, because for a soft photon every finite energy interaction looks like an infinite contact interaction because it cannot resolve any hard scheme. So this is what gives this UV divergence effectively, a new UV divergence, and we will see. I mean, it comes up in the computation itself. So let me maybe I can quickly tell the real basis for this divergence. Suppose I do this computation through this procedure. So I have let me just say there was some source which puts some momentum, and I'm just computing this thing, and I say using all this what will I get if I use SH to compute this thing, and this comes at one loop, and this turns out to be the following, just from the one loop computation. This is the answer we get by using the S hard for this process. So this is the Dyson computation, and this soft Wilson line gives us an additional contribution which is precisely this. Now you see that for small l these two exactly cancel. But this has a different, a large L, the UV divergence, even though they're log, their different coefficients are different. So we got a new UV divergence coming from here.
I think I was spacing out. You explain
sir.
why you should expect a new UV divergence.
Yeah, the new UV divergence we are expecting because of the fact that, all the dynamics that is taking place between 0 and minus infinity or 0 and infinity, it only has soft photons. And soft photons cannot resolve any hard scale. So any finite energy interaction looks like a contact for a soft photon.
Thanks.
And so, that's the reason. I mean, that's effectively the reason.
That first part of the contour.
Exactly, first and the last part of the contour. So, and the explicit evidence is this, literally this computation. If you do using SH, this is the answer we get, which is IR finite, but has a new UV divergence compared to the standard estimation.
But not in the first part of the contour, there were no matter interactions.
Well, the matter line was there, so that is the singular Wilson line, right? There was a matter particle which was sourcing this A. And so that's,
So
it's
you're
a.
saying the A interaction between matter, medium,
Exactly, exactly, because A is so soft for it, like every matter, yeah, exactly. Matter looks like infinite energy in some sense. So that gives the, I mean, this is the, you see, this is where we see, because if L is soft, we are, the difference between these two terms is that wherever there is a, L square is smaller compared to P1 dot L. So we are integrating here all over the L, but so you see this term is coming from the asymptotic dynamics, which means that as soon as there is a matter particle with momentum P1, for L it looks like infinitely large momentum, and that's what you see. So this is the actual answer for this using this Schwartz and Hoff's.
This is good. Your calculation.
Yeah, I mean this is they have much more complicated calculation. This is a computation they do in this is their computation, but they have done so many more sophisticated ones. This is a baby one they have done, but we would like to see that. So this is the amplitude one amplitude. We would like to see whether. So this shows that it is IR finite, but this is still a scheme dependent object. So we would like to see that at least it satisfies some criteria of this type, that at least it has a good check with the IR safe observables. That it matches with what we expect by IR safe. And the one example we will show is play with this semi-inclusive cross section that Ashok has proposed. Yeah. Okay, and then if I have time, I will discuss the connection of this with this soft Vacuua, which Abhijit also mentioned, moduli and asymptotic.
I mean, we can manufacture time.
So maybe I can.
Questions on Zoom audience?
No one is there. I think.
So everything okay?
No.
So, hello, is this something that before this Schwartz and so on, there was this cross-section thing that you told us about that it's IR finite. That was to say that we can calculate S matrix elements, but we don't know what the S matrix scheme is.
Inclusive cross sections we could compute, which were IR finite.
Now
there are many observables, KMOC, inclusive, semi-inclusive.
right, all of them computed
My usual estimate.
Right.
Yes.
But now the point of this I thought was to define the S matrix.
Exactly.
Not just the S matrix elements.
Exactly.
They're saying the S matrix defined this way is also scheme dependent. So it's not.
In the UV, but this we have to discuss. It certainly is IR finite, but the point is that it's scheme dependent. So one question we can ask is that, is it at least capturing the class of observables we know it should capture for it to pass a definition of a good S matrix? If it doesn't even agree with this, then there is already a problem, right? So, in light of the fact that it's not a scheme independent object, we should subject it to some criteria. And so this will be some data points for us to compare.
But even if that happened, you would still have some problem with the fact that this is scheme dependent. Right? Like that you couldn't define an S matrix which.
Yeah, but we have to discuss. I guess we could say that it's. I don't know if you can do better if you start with effective field theory to regulate IR modes, right? We should discuss this. I don't have a very good answer, but maybe when we write down the actual thing with the UV divergence, I mean, when we evaluate this, we will see that you could always say that I do wave function renormalization of this S matrix, but that depends on the scheme now you choose, right? So, but this is I'm not very clear about this also. Like, what to do with this? This seems inevitable. Huh? Yeah, go
It's
on.
one way of understanding the UV divergence that you had this particle which you forced to go up
Yeah.
and then come down along the same path, and then they're very near to each other. I mean, you have this Wilson line that
Yes.
goes up,
Yes.
and then you have a particle coming down. So
Exactly.
you've got stuff that's going more, retracing its trajectory more or less,
Yes.
and that causes a divergence.
I think so. I think effectively, yeah. I think so. I would say it can be also clearly seen if we forgot the S matrix definition and just look at the soft collinear effective field theory computation, where this is a theory for soft physics, but there are always UV divergences because of the fact that every finite energy interaction is replaced with a quantum. So we could always say that if I had a scale in the theory like the impact parameter, then I could always say that I'm going to regulate this L with some. If I have a physical scale in the theory, but that would be same as putting some cutoff on the, like a Kulishpati maybe put delta. So yeah, I think this is an issue that I don't have very good understanding. So right now the point is that, as we will see that even this is not clear that this actually passes this test. So I think it passes this test, but Ashok thinks it doesn't. So we will discuss this. And I think the main interest here is that in string amplitude, as Ashok has shown, that there is a definition of IR finite S matrix, which is completely independent of all these ambiguities, and also maybe one can do better in PFT.
I'm going to embarrass myself because something
No.
I haven't understood, which is normally we use the LSZ formula. We compute expectation value of 4 operators labeled by 4 points, and we get an S matrix where we do some stuff. What is the replacement of phi of x in that procedure here?
Okay.
Phi of x has a Wilson line attached. Where does that Wilson line go? If I just give you phi of x, there's no k.
Yeah, you're right. There is exactly. I think there is a
there's a key in the LSF one because you have to convolute the phi with the wave packet.
So you're saying I take phi x?
Okay. Yeah. So one solution is just to go to momentum space, but I'm hoping that there will be some in position space that you could replace given an insertion here, you'll send a Wilson line in space along some direction.
But the point is that if you give me a field, the soft photon is not coupling. I mean, it's only coupling to the.
We'll talk about K in 2 minutes, but first in position space.
I think it's going towards the collision region.
Wasn't it going to infinity? Oh, you mean whichever direction the collision is. It goes to infinity in the opposite direction. Collision. So you have to know where it's going to collide.
Because it's an inverted contour, it's going back to time equal to 0.
I think that exactly. I think that. Sorry, I'm getting a little confused. I mean, I agree that the point is that if you allow me to label. If you allow me to label.
I was thinking that maybe you can connect it to the other guy through the collision region, so that the whole thing would be gauge variant giving QCD. But sorry, go ahead.
No, I was saying that if you so you give me a velocity v. Okay, maybe I don't know if this will answer. Give me a velocity v and take a let's take a projection. Let's take some Dirac field psi. I don't know how to do for scalar because I want to label my field with a velocity field. So I'm saying that if I take this, we call it psi vx, then this psi v is going to be labeled exactly by the soft Wilson like we talked about. So somehow, because what is happening in soft collinear effective field theory is that we are replacing, what we are saying is that for each scattering momentum, we have an auxiliary field which is localized, matter field which is kind of localized in this direction. I mean, we are addressing those. I have to think a little bit more to say what, there must be an answer to your question, but I am not able to immediately think about it.
Now let's go to momentum space, like Omkar was saying. So say we were in momentum space.
Yeah.
Now there's a clear direction.
Exactly.
But there's no trajectory.
Yes.
So it's like you smear over Wilson lines.
Yes. Sorry. So you're saying that so that's what I'm saying. So you give me any field which is labeled by our velocity vectors, like in this way, for example. Then this is going to be just labeled by the Wilson line, exactly the one that we worked through. Soft dot D.
So if I think of it in terms of Wilson lines, there's a Wilson line with a different direction, but no definite location.
Exactly.
Just summing over all.
Exactly. So if you have, so the logic here is that you have finite number of particles, then you kind of attach a fiducial field with each direction, and then you dress each of these fields with a Wilson line, the way you would dress matter fields. But somehow you have to pick these directions.
Yeah. So you're saying in momentum space, there's a clear direction.
Yeah.
But it's not a localized Wilson line, but that's okay.
Yeah, it's a localized Wilson line in this soft collinear effective field theory because there the matter fields are labeled by some velocity vectors.
So you need it to be localized in space also in order to cancel divergence, right?
No, it should not. It should actually be very non-local, right? Soft divergence we are cancelling.
It should be the opposite of what the particle wave is. The particle wave is smeared out.
Exactly.
No, so I don't understand I understand Wilson line making something gauge invariant in position space. I have some psi of x and I multiply that by some Wilson line coming from infinity or wherever it is.
Yeah.
What's the momentum space equivalent of this statement? I mean,
No, so
once you tag on that Wilson line,
yeah.
now you can do a Fourier transform of this. What does it mean? What sense does it make?
Say that again.
So I'm saying that Shiraz's question is that in LSC,
Yeah.
I look at the gx1, x2, x3, x4, phi x1, phi x2, phi x3, phi x4.
Exactly.
And in that, perhaps I would attach a Wilson line to each one of them.
Exactly.
Wilson line infinity x1 multiplied by phi x1. Wilson line infinity x multiplied by phi x2. I insert all these guys, let us say. That's one possibility. But
Yes.
that's not how you are attaching this, mu k kind of guys.
That was attached to each velocity. Each velocity.
Velocity. But where is the velocity coming into this game?
Because we are always attaching them to some particles moving freely in space with momentum p. So we are looking at late time asymptotics.
Yeah.
And we are saying at late time you give me particles, they almost become free modulo, they have these showers of soft photons attached to them. And that is captured by this Wilson line.
Gautam, the way I'm thinking of it is this. That you've got these trajectories, and then you can't Fourier transform like this. But you can Fourier transform the end points of the trajectories. So think about, in 4-dimensional space, a 3-parameter set of Wilson lines. All in the same direction. Parallel to each other, but at different endpoints. So those are all Wilson lines, and then you can Fourier transform there. This is the wave. This is the direction the particle is moving.
Yes.
This is the wavefront. And you're Fourier transforming along that wavefront.
Yeah, okay. Actually, that may be more, I think that may be a more precise way to look at this. Exactly.
Right? Because anyway, particle states are labeled by their spatial momentum. Because time is determined by quick wave motion. So particle wave state is labeled by spatial momentum. So it's the same kind of Fourier transform.
Yeah, I think that maybe I'm also forgetting. I think there is a good. As Shira is saying, and there is we can write this in this position space thing. I'm forgetting now how the thing goes. Yeah. One thing I can say that if you did a expectation value of some phi x, Shira was asking phi x1, phi x2, but again this will not really satisfy you guys. And then you have clusters of momenta. Let me say p1 dot p k. These are clusters of some momenta, and then there is one soft momentum k. Then this expectation value is same as not having k and dressing this with this dressing these fields with Wilson lines along p1, p2 like that. I hope that. So this is same as we dress each of these with Wilson lines, where each Wilson line is coming from this momenta picked by the hard particles, and we remove. This is one way to write the soft factorization where you're looking at matrix elements of local operators. I'm not remembering the exact form, that's why I'm a bit hesitant. Maybe tomorrow I can tell you. So this is given in this Schwartz, and this was derived by Schwartz and file in this remarkable paper called Hard Soft Collinear Factorization.
Do they have a proposal for QCD?
Yeah, it's for QCD. So this is a factorization to all ordering perturbation theory in QCD.
The same definition of the S matrix.
No S matrix. The S matrix is more complete. I'm saying that there is a way that, okay, I'll tell you. There is a thing, so this is, even if you just for a minute forget S matrix, you can ask the following question that, can you isolate infrared and collinear divergence from finite energy contribution in a particular amplitude? And roughly speaking, the picture is the following that they prove very rigorously is that to any ordering perturbation theory, QCD amplitude, you can think of it as you can break it into what you call hard amplitude. Then that's some jet function which is like capturing the collinear part of the divergence, and then soft part which is emitting soft gluons. So this can be quantified to any ordering perturbation theory in QCD. This statement, only this statement.
But this can be rephrased as a dressing for us.
Yeah. So now the hope is that this one, it is this which gives them a motivation to look at this kind of stuff even in QCD.
Okay.
Yes.
And
So they have an answer. Yeah.
And how does that look? There's not just a Wilson line dressing.
I should look. I mean, it is a non-abelian type of Wilson line, complicated, right?
But didn't you say that the answer should be some e to the e to the?
Yeah. So it's non-abelian with when each soft guy is also addressed by other. But I don't remember the form. I should look at it.
Or some recursive.
Yeah, it's some recursive thing. It's complicated recursive thing. Exactly. So you are going. If you go to some ordering perturbation theory, you can stop somewhere. So if you just go to alpha square or something, you stop.
But there is a systematic.
It is infinite sum. Definitely, it is exponential of exponential.
Okay.
Yeah, there is a. Well, the organization formally was already given by Catani and others long back. Or how to write this exponential of exponential formally.
Okay.
But that can be also put in this form formally.
Something that is motivated by gauging lines. One can write it like that.
Yeah. Yeah, you mean through Wilson line? Yeah. So this is exactly how they write it. I don't remember in QCD exact form, but the exponential of exponential can be thought of formally as some kind of a soft Wilson line. Yeah. And the reason you can do it, actually it has soft and collinear effects included. So the hard S matrix should be IR finite and collinear. IR finite completely. Should not only not have soft divergence, also not a collinear divergence. So the reason you're able to do it is because you're able to isolate dynamics which gives you this guy and this guy, and kind of compensate for it in these other regions. So because they have this exact theorem, they could try to do that.
You'll talk about it.
No, this is above my pay grade. I mean, this is my knowledge. Yeah.
So one more comment about this Wilson line. Now, a Wilson line along space needs renormalization.
Yes.
So it may say that it's a unitary operator, but that's just
Yes, exactly.
You need.
Exactly. I felt that is what could be one way to look at UV divergence of this also, but I don't know exact connection, but that is what I was thinking. Yeah.
I was wondering about unitarity. Okay. I mean, like for instance, you take some. These are calculations that once done. Then they just start blowing up. Right?
Yes.
Okay. However, maybe your smear Wilson lines are. If you smear them in space, maybe they don't require along momentum.
Sorry, I thought the individual arms were divergent.
Exactly. Yeah, the whole thing is.
No. But I'm saying UV divergent.
Oh, UV divergent.
They're just you require renormalization to define the operator. If you just take a Wilson line like this, right? So it's formally a unitary operator, but it has divergences. So the operator you deal with is some number times that operator, which is then not even formally unitary. Okay. So for instance, the place I've encountered this is looking at holonomy operators and gauge theories.
Also this hexagon, I mean the Wilson loop type, Wilson line type computation, Maldacena and others, right? You get discussed
anomalous dimensions. Right, but these holonomy operators and gauge theories, they look unitary.
Yes.
But if you define them at some point in space,
yes,
there's no sense. There's no good sense in which they are.
Yes.
In quantum mechanics.
Yes.
Okay, because of the renormalization.
Yes.
I mean, okay, they're unitary, but they're infinite.
Yeah.
And then you make them finite, and then they're non-unitary. However, the guy that is smeared over the circle, over the S3,
Yes.
that starts behaving, looking more or less genuine to you. And this is the kind of thing you're doing. You're smearing over K.
Yeah.
So I'm wondering whether that will actually help. That we should just not think in position. Think smearing.
But even, I mean, sorry, so are you saying somehow that we may be able to understand this divergence we encounter?
The divergence I feel is because you're retracing trajectory.
Okay, I see. You are saying somehow we shouldn't do that.
You know, I should or should not, I don't know, but I feel that is. But the main interest for me is unitary.
Yes, I understand. Yeah.
And perhaps your formal argument about U is actually correct because of this smear.
Yeah, so SH is definitely a, so what we want to check is that if you choose a scheme to make it UV finite also, this extra divergence, then whether it remains unitary or not, right?
Yes, you're saying before you can ask that question, you have to deal with the finiteness.
Yeah, and then you can, I think this we can ask because they have these are log divergences, you do minimal subtraction. So you basically, what you're saying is you got SH, but there's some UV divergence, so I just multiplied with some wave function renormalization type stuff to actually cancel this UV divergence. This is going to be my physical S matrix.
Right.
And now you want to ask whether this is unitary or not, right?
I suppose.
Yeah, no one has asked, we can check this.
Yeah, it should be sort of easy, right?
In this case, yes, I think so. I mean, this is a question of just, because we know this expression, we have to really just stare at it. This we can do tomorrow.
Yeah, sounds very good.
More questions? If not, let's thank all of you.